So today what we're going to do is cover gases. And the first part of this is a repeat of what we did in class, where we're going to talk about the variables that influence gases. So, and those variables are temperature, pressure, and volume. And so we'll walk through that in class. This is just a review of those, and that's covered through here. With gases, there's a couple of concepts that are important to recognize and know. The first one is the concept of absolute zero. So absolute zero is the point at which there is no kinetic energy. So inside an atom, you no longer have electrons that are circling the nucleus. There's just no movement at all. So absolute zero is at a temperature of what's called 0 Kelvin. 0 Kelvin is negative 273 degrees Celsius, or negative 259 degrees Fahrenheit. And to get you an idea on how cold that is, deep space is about negative 270 degrees Celsius. So it's almost at absolute zero, but not quite there. So there are three temperature scales. One is Fahrenheit, which we use a lot in the States. If you go anywhere else in the world, most places use Celsius, even for everyday use. So you're, for instance, in Mexico or Europe or Asia, Celsius is basically what they use to record temperature, and it's not Fahrenheit like they do here. And I love this graph here. It's kind of comical when you look at Fahrenheit. For us, 0 degrees is just really cold outside. And again, in Nebraska, we always have a couple days of 0 degrees. 100 degrees Fahrenheit is just really hot outside, and we always have a couple days that is above 100. For Celsius, 0 degrees is actually fairly cold. It's not quite as cold as 0 Fahrenheit. It's just fairly cold. But 100 degrees Celsius, or the boiling point of water, you will be dead. And then for Kelvin, 0 degrees Kelvin, you'll be dead. 100 degrees Kelvin, equally dead. I always find this interesting here, how this Walgreens recorded a temperature of negative 196 degrees Fahrenheit. Man, we better hope we never have that. So here are the three gas equations that we're going to spend some time on. So the combined gas equation is pressure 1, volume 1, divided by temperature 1, equals pressure 2, volume 2, divided by temperature 2. You'll use this equation when you have a gas under certain conditions, and then you're changing items about that gas, and you want to know something new about it. So it's the same gas. We have initial conditions, and then we have new conditions for it. Ideal gas is when you're trying to find out an item about a gas, and that's PV equals nRT, where P equals pressure, V equals volume, N equals moles, R is the universal gas constant, which I'm going to go over on the next slide, and T equals temperature. And then the litter box equation is this symbol here is mu for molar mass equals D, which is density, times the universal gas equation of R, times multiplied by temperature, which is T, divided by P. This is called the litter box equation because the molar mass symbol sounds like mu, or like close to meow, and then it's mu equals dirt over P. So what a cat does in a litter box. Okay, R values. So the universal gas constants are set up to make the equations very easy to work with. And the only thing you need to know about R values are you have to pick the R value that matches the pressure that you're working in. For any quiz or test, I'll give you guys the R values. So those will always be provided for you. And you just need to pick the correct one. So if the gas is in ATMs, you're going to want to use ATMs. If the gas is in millimeters of mercury, you want to use millimeters of mercury. If the gas is in kilopascals, you want to use kilopascals for that. This slide here is very useful because I put all the different variables on it. To me, the biggest issue that students make when it comes to gases is they mix up the variables. So they think like a volume variable is pressure or vice versa. So always, always, always make sure to keep that separate and organized in your mind. So pressure equals P. And again, 1 ATM is 1 atmosphere. and that's going to be equal to 760 torr, or 760 millimeters of mercury, which is equal to 101.3 kilopascal. Temperature is T. It's always in Kelvin. You'll take the temperature of Celsius and add 273 to that. Volume is V, which is always in liters, and moles is N, where you're going to use the mole map if given the number of particles are grams. The gas constant is R, which I'll provide you, and that was on the previous slide. Molar mass is mu, which you can get from the periodic table, and then density equals D, and that's always going to be grams of the gas divided by liters. So next thing I want to talk about is standard temperature and pressure, or STP. Standard temp is 0 degrees Celsius, or 273 degrees Kelvin. 1 atm equals 760 millimeters of mercury, which equals 101.3 kilopascal. 1 atm equals the pressure at sea level and freezing point of water. So again, they wanted to have a pressure point that made sense. Given sea level is on every continent, and given water is fairly universal since we are a water planet, they just decided that was the best course of action to go. So now what we're going to do is do a series of problems. I'm going to walk you guys through this. So here is problem number 1. And anytime you read a problem, the first step you want to do is determine what gas equation you want to use, and then fill everything in. So for problem number 1, it says that the starting pressure of a gas is 1.0 atm with a volume of 1.0 liters. If the pressure goes up to 4.5 atm, what will the new gas volume be? Well, when I look at this, it talks about old variables and new variables. So it's an indication that we're going to need the combined gas equation. P1V1 over T1 equals P2 V2 divided by T2. And again, the temperature is not going to be needed for this because temperature was not talked about in the problem. So you don't need it. So when we cross temperature off, we're not going to be left with P1 V1 equals P2 V2. So then what we want to do is just fill in all the variables. And pressure 1 would be 1.0. Volume 1 is 1.0. The new pressure is 4.5. And then the new volume is what we're trying to find. So we're going to make that equal to V2. So then what's going to happen is I'm going to plug everything in. So P1, V1, P2, and V2. And then what we're going to do is we're going to get V2 by itself. So we'll take P1, V1 divided by P2. When you do that, you're going to get 0.22 liters of gas for the new pressure. Let's move on and do problem number 2. So if you start with 15.0 grams of methane, which is CH4, at a pressure of 2.5 atms and a temperature of 315 Kelvin, what is the gas volume? Well, you notice we have a gas under one condition and one condition only, and we're trying to find out a variable about that. So it would make sense that for this one, we're going to use the ideal gas equation of PV equals nRT. So on this slide here, I have everything set up. The pressure that was provided was 2.5 atm. The volume that was provided is V, which is what we're trying to find. The number of moles will be 15.0 grams. Molar mass of CH4 is 16.04. Sorry, this is on the slide. It should have been, but this comes from the periodic table. And that'll give us the number of moles of 0.935 moles. Because I'm in ATM, I'm going to use the gas constant associated with ATM, which is 0.0821 liters times ATM divided by mole times K. And then my temperature is going to be 315 Kelvin for that. So when I plug everything in, this is what it looks like. I need to rearrange everything to get volume by itself. So volume is going to equal 0.935 moles times the R value multiplied by the temperature divided by the pressure. That's going to give me a volume of 9.7. I think as you can see, as long as you have the variables straight and you pick the right equation, it just becomes a very simple calculation of multiplying and dividing to get your final answers. So gas law problem number 3, if you have chlorine at a temperature of 310 Kelvin and a pressure of 710 millimeters mercury, what is the gas's density? Given it's asking for density, that's a clear-cut sign. We're going to be using the litter box equation, which is mu equals dRT over P. When I plug everything in, my molar mass is going to be 70.90. I know that because the problem gave me Cl2. So I go to the periodic table, and Cl is 35.45. So when I multiply that by 2, I get 70.90. The temperature was provided as 310. The pressure provided was 710 millimeters of mercury. Because I'm in millimeters of mercury, the R value is going to be 62.4 liters, millimeters of mercury divided by mole times K. And then we can go ahead and plug everything and solve for D. So when we do that, we're going to have 70.9 times 710 divided by 62.4 divided by 310 will be density, which is going to be a density of 2.6 grams per liter for that one. We'll spend a lot of time covering gas problems. This is just an introduction to that. And we'll work on this and be good to go. But you guys will definitely have homework and also quizzes that will be based upon manipulating and utilizing all 3 gas equations. So now back to concepts. So we're going to talk about the concept of diffusion. So diffusion is the speed that gas molecules move. And a good analogy for this is if I had a bottle of cologne or perfume and I'm spraying it in the classroom. I think you all would agree that the students sitting closest to me would smell the cologne or perfume first, and then the students that were furthest away would smell it last. But eventually they would smell it because those gas molecules are moving constantly throughout the air. And so what happens is how fast can you actually smell something from the opposite side of the room. And so that's the item of diffusion. And again, the smaller the gas molecule is, the faster that gas molecule will diffuse. So, for instance, helium, which has a molar mass of 4, is going to diffuse much faster than a gas like argon, which has a molar mass of roughly 40. Effusion is another concept where it's speed of gas molecules through a pinhole. So it's how quickly, will a latex balloon deflate with different gases. So you have like a small opening, and then it's like, okay, how fast can the gases leave from the container it's in to the outside world? And again, the smaller the gas is, the more efficiently or the faster it can effuse. So going back to our example, hydrogen, which is only 2, can effuse much, much faster than something like xenon, which has a molar mass of 131.29 for that. Next, I want to talk about Dalton's law of partial pressure. Dalton's law of partial pressure is very straightforward. What it is that if you know the individual pressures of all the gases in the container, you can then know the total gas, or you know the total gas and you know most of the pressures that are in there, but one, you can then find the unknown gas. So here is just a simple Dalton's equation. We have a mixture of oxygen, hydrogen, and nitrogen gases. They exert a total pressure of 278 kilopascal. I know that oxygen has a total pressure of 112. I know that hydrogen has a pressure of 101. And what I want to know is, what would the partial pressure exerted by the nitrogen be? So when I go to my partial pressure equation, P total is going to equal pressure 1, pressure 2, pressure 3. We have P total, which is 280 kilopascal. We have the pressure of one gas is 112. The other gas is 101. And so when we subtract both of these from the total, that's going to give us our pressure total for nitrogen. So what's going to happen is you'll take 278 minus 112 minus 101. That'll get you a pressure of 65. So 65 kilopascal is the partial pressure for nitrogen on this. So let me go and talk about this. So we'll be working with phase change diagrams. So a phase diagram is really useful. And what it tells you is for any pressure and any temperature that you have for an object, you can determine what state of matter that object is in. So for instance, if you look over here at a temperature of 50 and a very low pressure, we'll say 0.003, this is going to be water vapor. Or if we're at a pressure of 1 and a temperature of 80 degrees Celsius, that water is going to be liquid, or just called water. And if we're down here at negative 20 and we're at a pressure of, between 1 and 218 ATMs, we're going to have ice. So it kind of walks you through what states that you would anticipate that would occur depending on the temperature and pressure of the object. And then triple point is the point in which all three are together. All three states exist in the same place. So water, ice, and water vapor are all going to be triple points that are going to exist at the same. So basically at this point, at 0.006 and 0.01 degrees Celsius, that's going to be the triple point for water, where ice, water, and water vapor all exist at the same point. Critical points are anything starts to break down. So you have these firm lines between the two. And then once you get a high enough temperature and a high enough pressure, it kind of starts to break down where it's a little bit fuzzy on what phase that you might get. Now, all of gases, to make the equations easy, to make the constants easy, are all based upon this notion of kinetic molecular theory, or KMT. KMT is assumptions to make gas equations easy and straightforward. So gases act close to KMT, except under extreme pressure and or low temps. And we're lucky because most of the time gases are under reasonable pressures and reasonable temps. So therefore KMT matches, and so it's much easier for the calculations that we're doing. So for gases, these are the items about KMT that we hold to be true. 1, it behaves like hard spheres in constant random motion. 2, it's going to move in straight lines until collisions occur. 3, the volume is empty space. 4, there are no attractive forces between gases or container walls. And again, to be clear, none of this is true. Gases are not hard spheres. They don't move in straight lines. The volume is not empty. They are attracted to each other. But again, at reasonable pressures, reasonable temperatures, we can assume that these are not strong enough factors to deviate from the gas equations. The other items that match up with KMT is collisions between gas molecules or wall are perfectly elastic. That's not true. Again, you're going to lose energy as you collide with stuff. So you're not going to have a perfect transition of the energy from one gas molecule to another, or one gas molecule to the wall. No energy is lost when gas molecules collide. Again, not true. There is. And then average kinetic energy of gas molecules collection depends only on the gas temperature. And so again, we just align kinetic energy with temperature to make that work. As I stated, none of this is true. The collisions with gas molecules in the wall are never perfectly elastic. Energy is lost, and then kinetic energy is more than just the gas temp. But again, under normal conditions, we can make these assumptions to make the equations easy to work with and to do it with just the simple gas equations that were covered earlier in this video. Now, the most ideal gas behavior is the behavior that overcomes the conditions on the previous two slides the most, and that's going to be high temp, low pressure, and low number of moles. The biggest thing that influences gases is that they get close and can interact with one another. So if you can find conditions that they are not close to each other and they don't interact with each other, that's going to give you the most ideal conditions and match up ideal with reality. The example I'll give you to learn this is an ideal gasification. You prefer to have warm temperatures, very low pressure, where everything is smooth, everything's straightforward. You're not trying to meet deadlines or things like that, and then probably a low amount of people or moles. So you think about an ideal vacation you can have: Paradise Island, no pressure, just you and the people you want, no lines, and then to enjoy the things that you enjoy doing. The worst vacation ever would be the opposite of that: low temp, high pressure, lots of people. So these are the conditions on which the gas laws will fail, because the molecules can then come in contact with each other, and the interactions of the molecules become stronger because they do come in contact, and then KMQ breaks down and the ideal gas equations break down. This is going to be a common question I ask, so just make sure you know what's the most ideal and least ideal. Again, least ideal, worst vacation: cold, high pressure, lots of people. Best vacation: high temperature, low pressure, few people. So I have this short slide I'll show you guys. This is just a short video done by Mythbusters, actually, where it talks about why our voice changes with helium, and then they use a heavy gas, and it has the opposite effect. So that's all I have. Again, these notes will be a great reference for you as we work through the unit. And as always, if you have questions, you can ask in a class, and we'll go through some of these items in class.